In the final part of this titration problem, we're going to calculate what the pH is after we've added 20 mL of 0.5 molar HCl to our original 40 mL of 0.2 molar ammonia. So as always, we begin by calculating the proportions of our weak base and its conjugate acid after addition of the acid. So we know that we began with, in our 40 mL of our weak acid, 0.008 moles of ammonia. So now we have to calculate our moles of H+, and so we're adding 20 mL, and the concentration is 0.5 moles per 1 litre or per 1000 mL, and so that works out to be that we're adding 0.01 moles. So in this case, what's happened is we are past the equivalence point. We're adding more strong acid than weak base that we started with. So we're going to use up all of our weak base, and we're going to use up some of our strong acid, and then we're going to convert all of our weak base to its conjugate acid. So at the end of this, we will have no weak base left. We'll have a little bit of our strong acid left over, and all of our weak base will have been converted to its conjugate acid. So the fact that we have no weak base at all, we only have the conjugate acid, tells us that we're going to have to do a Ka ice table. So we can go ahead and set up the Ka ice table for the ammonium ion. So NH4+ is in equilibrium with NH3 and H+. Now when you do an ice table, you got to work in molarity, so we need to calculate our initial concentration of the ammonium and H+. So the concentration of our H+ to begin with, we know that we've got 0.002 moles, and that's going to be dissolved in the 40 mL that we started with plus the 20 mL that we added. That needs to be in litres, so that works out to be 0.002 divided by 0.06, and so that is 0.0333. So our initial concentration of that is 0.0333. Now we do the same calculation for our initial concentration of the ammonium ion. So that's going to end up being 0.008 moles, because that's how much of that stuff we've got. And again, that's going to be dissolved in our 60 milliliters. So, oh wow, look at that. It just looks like it was 4 times what we had before. So I'm just going to times my previous answer by 4. And that ends up being 0.1333. 0.1333. This is 0. So now it comes into equilibrium. We don't need any of these calculations down here. So what's going to happen is it always moves towards the zeros. It can't move towards the left because we don't have both of the products present. This will go down by x, this will go up by x, and this will go up by x. So when we get to equilibrium, that's going to be 0.133 minus x. This will be x, and this will be 0.0333 plus x. Okay, so now I can keep working. Now Ka for the ammonium ion, we calculated it before. It is 5.56 times 10 to the minus 10, and that's going to be equal to our product concentrations over our reactant concentrations. And because it's so much quicker, I'm just going to use the solver to solve for x. So I'm going to go into my solver and I'm going to get an answer for x. It turns out that that number is very, very small. It is 2.226 times 10 to the minus 9 moles per litre. So my hydrogen ion concentration is going to be 0.0333 plus x, and the negative log of that will give me the pH. So pH equals negative log of 0.0333 plus my x, which I saved into my calculator previously. So there's going to be negative log of 0.0333 plus x, close the parentheses and hit enter, and I got 1.478. And it's acidic, right? Because I'm way past the end point.